In this video, I'm going to summarize what we've learned about game theory in the past weeks. These are the things that you absolutely need to remember, especially if you're not taking any other game theory courses. Alright, so let's summarize what we've learned over the last few weeks. Game theory studies strategic interactions among players. These strategic interactions are called games. Simultaneous games, also static games, are usually expressed in normal form. And then, if we have two players, in matrix notation. Sequential games, also called dynamic games, are usually expressed in extensive form, in the form of decision tree notation. A Nash equilibrium is a combination of strategies for each player such that no player has an incentive to unilaterally, meaning alone, change their strategy. Or you could say, a Nash equilibrium is a system of mutually best responses. Or you could say, a Nash equilibrium is a strategy profile where no player can do better if they are the only player to deviate. All these three definitions mean exactly the same, so you can use whatever you can remember more easily. More important, however, is that you understand the meaning behind them. It is also important to realize that Nash equilibria are not restricted to games where the players choose from discrete strategies, like in the examples here, where players always chose between left and right, up or down, things like that. For example, imagine two firms competing in a market and setting prices which determine how much of the market demand each firm can capture. This would still be a game, because it's still a strategic interaction. Here the prices are the firm's strategies, but they can set them anywhere between 0 and infinity. To solve these kind of games, we will need to create response functions from the profit functions and find the Nash equilibria this way. This is something you will do in the second part of this course. Next, what is a strategy? A player's strategy consists of a player's moves, decisions or actions at every possible point in the game. A strictly dominant strategy gives a player a strictly higher payoff than any other strategy, holding the other player's strategies constant, irrespective of what these strategies are. A strictly dominated strategy gives the player a strictly lower payoff than another strategy, again holding the other player's strategies constant. If there is a strictly dominated strategy, that means there must be another strategy that strictly dominates the dominated strategy. We can use the iterated elimination of dominated strategies to simplify games in normal form. Here is an example. First we eliminate the dominated strategy down. Now the strategy right is dominated, so we eliminate that one. Now up is dominated, so we eliminate up. Next, center is dominated, so we eliminate center. And end up with the Nash equilibrium middle left. Don't forget that the iterated elimination of dominated strategies also works with mixed strategies. How do we find Nash equilibria if we don't have dominant or dominated strategies? In matrix notation, we find Nash equilibria in pure strategies by marking each player's best responses. So here, left is best response to left and right is best response to right, so we have two Nash equilibria, left left and right right. A mixed Nash equilibrium is found by making all players indifferent between their strategies. In extensive form games, we find subgame perfect Nash equilibria using backwards induction. We start at the last decision nodes and work our way up to the initial node. Here the subgame perfect move is left, here the subgame perfect move is right, and for player 1 the subgame perfect move is right. So the subgame perfect Nash equilibrium here is right, left, right. There may be other Nash equilibria that are not subgame perfect, but they will contain implausible threads. However, there's no easy way to find them, you may have to look at every possible combination. What different types of games have we encountered? First, zero-sum games. In a zero-sum game, the sum of all payoffs is the same for all outcomes. So what one player gains, the other one loses. We have also encountered social dilemma games. In a social dilemma game, the Nash equilibrium is not Pareto efficient. One example is the prisoner's dilemma, where we have a Pareto inefficient Nash equilibrium in dominant strategies. We've also encountered coordination games. A coordination game is a game with two or more Nash equilibria in pure strategies. For example, the stack hunt game. In a stack hunt game, one Nash equilibrium is Pareto better, but also more risky. Here the Nash equilibrium stack-stack is Pareto better than the Nash equilibrium hare-hare, but by playing hare you secure an outcome of 2 for sure, whereas if you play stack you will receive 0 if the other player plays hare. Additionally, we've come across the Battle of the Sexes game. In a Battle of the Sexes game, each Nash equilibrium favors a different player. Finally, we have talked about information in games. Information in games can be complete, that means all payoffs, available strategies and players' preferences are common knowledge. Or information can be incomplete, which means that some players have hidden information about themselves or possibly the game. Here in the example, we see that player 1 does not know the payoffs of player 2. Additionally, we had perfect information. In perfect information games, all moves can be observed by all players. And the opposite to that, imperfect information, where some moves are unobservable by some players. If there's imperfect information, we define information sets which are decision nodes which contain the same information. In decision trees, these information sets are denoted by a dashed line, or an oval, or a rectangle. So these are all the things you absolutely need to remember, and if you do, you can honestly say that you understand basic game theory.